How would you feel if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you? A similar feeling was expressed by the famous scientist Rutherford about his alpha ray scattering experiment. Let's see what this experiment was. Our objectives are to study the experiment suggested by Rutherford to understand the structure of an atom, to discuss the conclusions drawn from the experiment, and to estimate the nuclear dimensions. Ernest Rutherford designed an experiment to verify Thomson's plum pudding model of an atom. Rutherford's idea was to fire energetic alpha particles at a piece of thin gold foil in a vacuum. At the suggestion of Rutherford, Hans Geiger and Ernest Marsden used the following experimental arrangement. An evacuated chamber contains a rotatable microscope which has a screen of zinc sulfide. Near it, there is a thin gold foil of thickness less than 1/1000th of a millimeter. A lead box with a small hole contains radon as the source of alpha particles. A narrow beam of alpha particles produced from this source is directed at the thin gold foil. The gold foil is chosen as it has a larger atomic radius compared to many other atoms, and it is easy to make into a very thin foil. After passing through the gold foil, the alpha particle beam strikes the zinc sulfide screen, where it is detected as a flash of light. Results of the experiment. Geiger and Marsden observed frequent flashes of light showing that most of the alpha particles passed straight through the gold foil. When the microscope was rotated through a small angle, they found that the number of flashes reduced considerably. However, when the microscope was rotated through large angles, to their surprise, they could still see some flashes even when the microscope was on the same side of the foil as the source. A typical graph of the total number of alpha particles scattered at different angles in a given interval of time is shown. Discussion. Alpha particle weighs about 8,000 times an electron, and alpha particles move with a velocity v is equal to 2 into 10 raised to the power 7 meters per second. Rutherford assumed that the only force acting between the alpha particles and the atom was the Coulomb electric repulsion. The backscattering indicates that the repulsive force has to be very powerful. This force could be provided if the positive charges, instead of being spread through the atom, were concentrated at its center. Moreover, as thousands of alpha particles pass without much deviation, this heavy mass must be located in a very small volume, and the rest of the space in the atom must be empty. Hence, Rutherford's experiment clearly rejected Thomson's plum pudding model. Rutherford proposed a nuclear model of the atom, in which the atom is composed of a tiny nucleus at its center containing positive charges. Nearly all its mass is concentrated in this nucleus, and the electrons are located some distance away. The electric repulsion between the nucleus and the alpha particle deflects these particles before they come close enough to the nucleus. Rutherford derived an expression for the number of alpha particles deflected through various angles. Tan theta upon 2 is equal to Ze square upon 2 pi epsilon 0 mb v0 square. Here, theta is equal to the angle of deflection. V0 is equal to the initial velocity of the incident alpha particle, which means V0 is equal to 2 into 10 raised to the power 7 meters per second. Z is equal to the atomic number of the foil atoms. For gold, Z is equal to 79. E is equal to the charge of an electron, which means E is equal to 1.6 into 10 raised to the power minus 19 coulomb. Epsilon 0 is equal to the permittivity of free space. Here, epsilon 0 is equal to 8.85419 into 10 raised to the power minus 12 farads per meter. And B is equal to the impact parameter, which is the perpendicular distance between the nucleus and the velocity vector of the alpha particle. From this equation, we can conclude that smaller the value of B, the larger the deflecting angle of the alpha particles and vice versa. The minimum distance R0 up to which the incident alpha particles approach the nucleus before being deflected is called the distance of closest approach. It is given by the equation R0 is equal to ZE square by pi epsilon 0 m V0 square. Rutherford assumed that the radius of the nucleus is small compared to the distance of the closest approach from the nucleus. The estimate of the nuclear radius obtained by him was equal to R is equal to 4.1 times 10 raised to the power minus 14 meters for the gold nucleus. To summarize, from the experiment of the alpha particle scattering, it is found that most of the alpha particles pass through the gold foil without much deflection, but a few of them deflect through large angles. Alpha particles being positively charged and having a large mass as compared to an electron could only be deflected if the positive charges were concentrated in a very small region at the center, which is now called the nucleus. Rutherford estimated the nuclear radius R is equal to 4.1 times 10 raised to the power minus 14 meters for the gold nucleus and suggested a new nuclear model of the atom. The main discovery of Rutherford's alpha ray scattering experiment was the discovery of a nucleus inside an atom. But the bright minds after Rutherford were also successful in probing what was the nucleus made up of.